Brendan Show, starring me, Brendan. Today, we're going to be talking about the magic of normal modes. Important because they can be applied in a large number of areas, from everything from construction, ensuring buildings have a certain type of normal mode, to music, where normal modes correspond to tone. We wouldn't have beautiful music if it wasn't for normal modes, to, as we will see, predicting the oscillatory behavior of molecules and their atoms. It's a very useful tool. A normal mode is when all parts of a system move with the same frequency and fixed phase relation. As in this graph, we have two functions that have the same frequency, but they have a fixed phase relation of pi. In the Wolfram math world, eigenvectors, which are related to normal modes, are vectors that stretch or compress by a scalar factor lambda, also known as the eigenvalue, when undergoing a linear transformation, like being multiplied by a matrix. This can be used to find the frequencies of the normal modes. As we will see, in some cases, frequency can be part of the eigenvalues. Now, the eigenvector equation is this right here. We have a matrix transforming a vector r, and that is equal to the scalar factor lambda times r. We can arrange it to be thus, and we end up getting this down here, and this is going to be very important later on. We should note that for r, the vector r, to not have a trivial solution, the zero vector, 0, 0, 0, that this term right here, this matrix, needs to be linearly dependent. If it was linearly independent, there would only be the trivial solution. So the problem that we are going to do is calculate the natural modes of a carbon dioxide molecule, which consists of one carbon atom and two oxygen atoms. They have their respective masses. The mass of oxygen is 16 atomic masses, and the mass of carbon is 12 atomic masses. Since there are three masses, that means 3 degrees of freedom. We are associating X, Y, and Z per each mass and each degree of freedom, but they're all they're all in one dimension. And their bonds we're just going to treat as springs with the same K constant. And what we could do then is use the potential energy equation for a spring to create an equation for the potential energy of the entire system, which is this right here. According to hyperphysics.phys-aster.gsu.edu, we know that force is equal to the partial of potential energy with respect to position. So because of that, we could get Fx, Fy, and Fz, which, if you apply that, comes out to this, this, and this. And we also know that force is equal to mass times acceleration. So for x, y, and z respectively, we get the m times the second derivative of the position. From here, we're going to make an ansatz, which means educated guess, and guess that x, or the positional function, is equal to x sub 0 e to the I wt. And when we take the first and second derivative, we end up getting that negative omega squared, not w, omega squared. So now we're going to take an ansatz, which means educated guess, and say that x is equal to x sub 0 e to the I omega t. And if we take the first and second derivative, we end up with the second derivative of x or y or z is equal to omega squared times x or y or z. So using that, we can plug that into our force equations. So we get this for F sub x, this for F sub y, and this for F sub z. So now what we are going to do is, because M sub O and M sub C, which correspond to oxygen and carbon, are different masses, they're different ratios of the atomic mass, we're going to plug those into the equations. And we're also going to bring K to this side, so that we have this form, and we're also going to take the coefficients and move them to the divide it and move them to this side like this. Now what we're going to do is set that coefficient equal to lambda, the eigenvalue, and just rearrange it into this matrix and scalar multiplication form of the vector, which is the same thing as the eigenvector equation that we saw earlier with r being x, y, and z. Now we need to rearrange it to get it into this form, and again we want this component or this matrix to be linearly dependent. So then what we're going to do is set this term equal to the determinant rather equal to 0. And we're going to take that matrix and take its determinant and set it equal to 0. And after a whole bunch of algebra, you end up getting 3 eigenvalues, which are, in this case, 0, 1 over 16, and 11 over 48. So we need to go through this 3 times with the different eigenvalues. We plug this into this, and we just get sort of the original transformational matrix. We row reduce that to get this relationship. And then this ends up being the eigenvector right here, and then the frequency of the first natural mode is this, which is just simply 0 because the eigenvalue was 0. I'm going to do that for the other 2 eigenvalues. For 1/16, you go through this process, you end up with this relationship and this eigenvector, and this is the second frequency associated with that natural mode, and then this is for the last eigenvalue, 11 over 48. Go through the same process, you get this relationship, which ends with this eigenvector, and this is the last frequency for the normal mode. So now that we have all of the eigenvectors and eigenfrequencies, we can add them together to form the ultimate natural mode frequency, which ends up being this. The A, B, and C are related to initial conditions, like the displacement of the atoms. And these ones are oscillatory, but this one is not. This one's translational. As you can see, there was a 0 frequency, so this one just really represents the molecule moving in space. Application of natural modes occurs very often in the real world. For one thing, in construction, they need to take natural modes into account according to Real Modes of Vibration of Building Structures by Henry P. Gavin. They need to calculate the natural modes of a building to ensure its stability.
Look at that. That doesn't look good.
In music, a string, the tones of, say, a guitar string are associated with its normal mode. And as we demonstrated, one can determine the normal modes for the vibration of the atoms within a molecule, which is extremely important to physics and chemistry.
And this is what we calculated, the 2 oscillatory modes of CO2.
References used in this presentation are as follows: Waves and Normal Modes by Matt Jarvis, Wolfram Math World, hyperphysics.phys-aster.gsu.edu, and Real Modes of Vibration and Building Structures by Henry P. Gavin of Duke University. Thank you, and have a good night.